method is to do 3 questions from every test and then 1 bonus that I just pick. So not a bonus question, but an extra. So it's it's 13
And
questions.
not 3 proofs, just 3.
So what I try to do for every test is 1 proof, 1 not proof, and then a third of my choosing,
Like what do you mean?
which is often a proof. But yeah, and then when I grade it, I toss your worst one. So I only grade your best.
Your worst, what, your worst test?
No, your worst problem on that test.
I see.
Yeah.
Get every single one right. Perfect.
You still get, yeah, the question is still tossed, but a question that you got 100 on got tossed, but you still make 100.
So if you're like really bad at a certain something, at a certain proof.
Well, you can practice that proof.
That would be, if you know you're bad at it, I would go ahead and practice to get better, right? Yeah.
Fortunate.
Did you put note cards on test 3?
I did.
Okay.
I did not give you your note cards back.
Okay, I'm thinking maybe I should go back to all the note cards and like, any ideas of what to do on the final.
Probably be a good idea to just look at your tests.
That too.
Because like you didn't know what was gonna be on the test when you made your note card, but once you have the test, you know what's on it, right?
Yeah.
But I'll give you your note card back if that's what you would like.
Yeah, I did not know cardinality was on the test.
I know that I told you it would.
It was on the test and I did not put it on my note card. And I was very, very upset.
Did you put it in your brain?
You know?
That would have been even better.
Yeah.
I tried.
Okay. But first, before we do the final, we have to finish this packet of material and do the test 4, 5, 4, 4. So,
I say we skip it on test 4.
I think you would probably want to be tested on the material for test 4 before. Yeah, you will. Wait till we do it. You're gonna want it. You wait till we finish this. Wait till.
Oh,
No.
even better.
No, especially for my math people, I need to know that they can put all this together. This is, let me inform you, this is math 330, right? It's not computer science. It's not cross-listed. It's a math class, yeah? So I've got to cater to my math people.
It's not Ruth, right?
It's major.
And Sky.
All right, so if they were to somehow magically disappear, we wouldn't have a final.
Whoa.
Whoa, hey,
Let's just not explore that.
let's don't, yeah.
Okay, y'all have your notes out ready to go? Yes, we are finishing this theorem, that all 3 of these things are equivalent, that A is related to B, that the equivalence class of A is equal to the equivalence class of B, and that the equivalence class of A intersected with the equivalence class of B is not empty. Okay, so we did on Thursday of last week, we assumed I and used that to show that I works. Today, we're gonna do I implies I, and then we'll do I implies I. So you got this string, a circle of implications here, which means that they're all equivalent. Okie dokie. So we are gonna do I implies I. So right now we're gonna assume, right now we're gonna assume that the equivalence class of A equals the equivalence class of B, and we're gonna use that to show that, I should be writing things down instead of just saying them out loud. Now we will show that the equivalence class of A equal to the equivalence class of B implies that the equivalence class of A intersected with the equivalence class of B is not empty. So we're going to let A and B be in big A. And suppose, sorry, Logan, suppose the equivalence class of A is equal to the equivalence class of B. Okay, so we need to basically find something in the equivalence class of A or the equivalence class of B. If there's something in one of them, then it's in, both of them, and so their intersection is not empty. But how do we know that there's something in one of them?
Do we get to assume that? Maybe
I don't know. Do we? Why?
we assume that AB is in.
Is A, yeah. Right. AB is in A, in big A. Is anything in the equivalence class of little a? What's the definition of an equivalence class?
I have been struggling with that. Like, I can do an equivalence class, but I don't know like what it is.
So the equivalence class is the collection of elements that are related to the element that you're looking at. So the equivalence class of A is the collection of elements from big A that are related to little a. Yeah, so you guys were doing these in WebAssign where it has like a set from, -3 to 6, and the relation is that 3 divides the difference of X and Y or something. And you've got to split these up into their equivalence classes. So you make A X or whatever. No. You pick a number and use it to be X, right? And then you're finding all of the Ys that would pair up with it. Yeah. So we need to know now what would be in the equivalence class of A. What makes something a relation? Let's start there. What makes something a relation?
It has,
That it is,
related to.
what makes something a relation? What makes something an equivalence relation?
Reflexive,
Oh,
transitive, and symmetric.
Okay, and what does it mean for an equivalence relation to be reflexive? For every X in A, X is related to itself. So that means for every element, it's in its own equivalence class. Yeah? Yes. So little a is in the equivalence class of A because A is reflexive, right?
Okay.
Since R is, I said A is reflexive, that doesn't make any sense. Since R is an equivalence relation, it is reflexive. Thus, A is related to A. So A is an element in the equivalence class of A.
Since A and B are equal to each other. A is in
Which means
when they intersect, A is in.
so it's not empty, their intersection is not empty because we have something in it, at least A, right, or B. The equivalence class of A equals the equivalence class of B implies the equivalence class of A intersected with the equivalence class of B is not empty. Let A and B be in A, suppose that's true. R is an equivalence relation, so it's reflexive. So A is related to itself. So A is in the equivalence class of A. And since the equivalence class of A is equal to the equivalence class of B, A is in the equivalence class of B. So it's in their intersection. So their intersection is not empty. Good. Yep. Questions about that? Questions? No, we're good? You good? All right, now we want to do I implies little I. So we will show equivalence class of A intersected with the equivalence class of B being not empty implies that A is related to B. So we're gonna let A and B be an A again, and we're gonna assume that the intersection of their equivalence classes is not empty. Okay, so what does it mean if they're if the intersection of those equivalence classes is not empty, what does that mean? It means that there's something in that intersection, right? Yeah. So then there is some X in A such that X is an element in this intersection. Well, that means that X is in the equivalence class of A and X is in the equivalence class of B. Where are we trying to get to for this one? What's the ultimate goal? What's the cue here? What's our goal? That A and B are related, right? So we have X is in the equivalence class of A and X is in the equivalence class of B, which means that X is related to A and X is related to B, right? Not quite.
Well, I thought it was if X is in A and if X is in B, then everything else. has to be the same.
Yeah, we're proving that though. Well, no, we got to show that we can get to just I, which is that A is related to B.
Well, if X is in both of them, then doesn't that mean that A is related to B? Because you have to X in both.
So you're saying the same thing that Whitney is saying, and yeah, that's the point, but we have to prove that. Yeah, the point is that these equivalence classes either overlap entirely or don't overlap at all, right? Yeah,
Right?
we're saying the intersection is not empty, so they overlap everywhere, right? That's what you're saying, but we're trying to prove that. Yeah,
And then not
Okay.
the group there.
we're close. We're so very close. I don't have A squiggle B written down, and that's what I need, right? Uh-huh, because we're trying to prove I, little I, way back up here. A squiggle B, but we're not there.
Oh.
How do we do that? How do we get there? I have X squiggle A and X squiggle B. I need A squiggle B. I can't apply the transitive property yet, can I? No, because the middle pieces have to be the same. Right now, they're not. Right?
We can flip them.
Why?
Because it's symmetric.
It's an equivalence relation, so R is symmetric. R is symmetric, which means that this can be written the other way, and then because it's an equivalence relation, it's transitive and you can smash them together. Yeah, and then we'll have A squiggle V. Yes?
Yay. Okay, now that makes sense.
That's the one.
Yeah, right. But R is symmetric. So A is related to X. Note. R is also transitive. So we have A is related to B. Therefore, the statements are equivalent. We did it. So what we are looking at and what you guys just said is that this is what this theorem implies is that for any two elements A and B, either their equivalence classes are the same, they can overlap completely, or they do not overlap at all. So those are your two options. Either they are the same or they are disjoint. And that's how these partition A by partitions, they're disjoint subsets whose union is the whole set. Okay. So a really good example of all of this is mod. Modular arithmetic, let's do it. So m and n are integers, d is a positive integer. We say that m is equivalent to n modulo d. And write m is congruent or equivalent to n mod d. If and only if, here's your definition, if and only if d divides the difference of m and n. Right, that makes sense. M minus this remainder term should be divisible by d, right? That's the, okay, so symbolically, m is congruent to n mod d. I hate writing mod and then a d, it's like my brain can't do it. D divides m minus n. So like in, I don't know, with examples, let's see if we can make sense of this definition. That is 12 congruent to 7 mod 5. So the way, I mean, maybe we can see that it is, yes, but do they have the same remainders? Kind of how I do that, but does the question to fit the definition is, does 5 divide 12 minus 7? Oh, that's 5, so yes. On that second one, does 4 divide a 6 minus a negative 8? No, it does not. The remainder of 6 mod 4 is 2, the remainder of 8 mod 4 is 0, so that doesn't work. They should have the same remainder, mod 4, to be congruent mod 4. That's what we're gonna prove in a minute. Okay, 3 congruent to 3 mod 7? Yeah, but does it make sense with the definition? Does 7 divide 3 minus 3? Yes, it does. Okay. So when we were doing this before, I wrote this down all over the place and told y'all we would come back to it later. And here we are. It's later, Bert. So we have, if you go back up to when we did these things forever ago, sometime here, I did these here, yes. I told you guys that this thing, which we hadn't talked about yet, because we hadn't really talked about equivalence relations yet, that this was the same as this. Yeah. And we are going to prove that now. Yeah, pretty cool. Don't let anybody get too excited. Okay, so we are going to prove that if we have A and B are integers and M is a positive integer, then A is congruent to B mod M, if and only if A mod M is equal to B mod M. So you can replace that congruence by just saying that they have the same remainder mod M, right? Okay, so we're going to do this. Are you ready? We're going to let A, B, B and Z, and M, B and Z plus. So this is an if and only if proof. So we're gonna do this 2 parts, right? P implies Q and then Q implies P. You good? Yes. Should I call these 1 and 2? I don't know. 1, that's an eraser. That won't help. 1 and 2. So this first part, we're gonna do 1 implies 2. So we are gonna assume that A is congruent to B mod M. We're trying to get to a place where we can write that A mod M equals B mod M. I'll write that right here, but you know, just ignore that it's in the middle of the proof since we didn't do any scratch work.
I thought it's if and only if,
It is. Why are you asking me that?
doesn't that mean the arrow is going both sides?
We're only good, we gotta do it one time.
Oh, we have to do it both, okay.
So we're trying to get to a point where we have A mod M equals B mod M. Now, we don't really know anything right now except for definitions. What does it mean for A to be congruent to B mod M? Yep. So by definition, M divides, I meant to write this in blue. What happened here? Here, I'll fix it. Nobody panic. Blue. Now it's blue. Blue. That didn't change. Blue, blue. So by definition, M divides their difference. So M divides A minus B. What does it mean? We're chasing definitions. What does it mean for M to divide A minus B? Yep. So then A minus B equals M times K for some integer K. Watch this. A is equal to MK plus B. All I did was move the B from one side to the other. But what did I make that look like? Oh, oh, no. But in the definition of odd fits this thing, and that's why it is that definition of odd. This is this number is a certain thing, and this number is a certain thing, and it's a theorem. It starts with a,
Oh, the Q or T.
yes, the quotient remainder theorem, yes. Yes, that's a line, yeah, but the quotient remainder theorem, you find, yeah, that it has an M and a B, you're right, MIK does look a lot like an X. The quotient remainder theorem says that every integer can be written as, you know, like with a quotient and a divisor and a remainder, and that remainder is stuck between 0 and the divisor, yeah. Or quotient, divisor, the divisor, yes?
Yes.
It's been a while, but yes.
That's why the odd thing works, because that remainder, that's why every integer is either even or odd, because that remainder, when you divide by 2, the remainder is either 1 or 0, so it's either even or odd for every number. That's the quotient remainder theorem, is how you prove that every integer is either even or odd. Cool, yeah? What?
That's not how we.
Yeah, it is.
It is.
I don't know. I think so. We can look back at no packets, but I'm pretty sure, because I don't know how else you would prove it. Okay. So by the quotient remainder theorem, we can write B in a particular way. And you're like, why are we talking about B? We'll get there in a minute. But by the quotient remainder theorem, there are integers Q and R such that B is equal to M times Q plus R, where 0 is less than or equal to R, which is less than M. But what does this mean about B?
Divides.
There's something going on there, right? If we divide B by M, what's happening with that? We have a remainder of R, right? This is how this works. The quotient remainder theorem says like, this is the quotient, this is the divisor, this is the remainder, yeah? Right? So then B is congruent to R mod M, right? The remainder, when you divide by M, is this integer or whatever, this integer R. Yeah? Okay. So B mod M is equal to R. Right, think about this, like that means that M divides B minus R, right? B minus R here is MQ, M divides M minus R, yeah, that's the definition there. B minus R, I mean, you get that, we're with me, yes, okay. So we have B mod M is R. We are trying to show that A mod M is equal to B mod M, so we want to show that A mod M is also R. Are you tracking that? We now have the thing we're calling the remainder mod of B mod M. We would like to be able to call that the remainder of A mod M also. Yeah? Are we okay or not okay? Oh, respond would be good. Are you good with this so far?
Yep.
Yes, tracking what's happening at least?
Yeah.
I'm not expecting you to come up with this on your own right now. We're doing it together for a reason. Are you with me? Okay. So I would like for you to consider A is equal to MK plus B. Remember, we did that way back up here. So what can we do now? That, yeah, B is MQ plus R, so just plug it in, right? B is MQ plus R. And then we are gonna factor an M out of this, right? So you're looking at K plus Q plus R. And we're done, right? A mod M, the remainder mod M is R. So we did the like first part that A being congruent to B mod M implies that A mod M equals B mod M. Now we're gonna assume that A mod M equals B mod M and show that they are, show that M divides the difference there.
It's gonna be a longer one.
No, this is shorter. This is shorter. This part's about half as long. Ooh, I'm gonna be tight for space too. Okay, so we're gonna assume that A mod M is equal to B mod M. So I'm gonna write this over here just for good measure. Don't do this in your own, like, don't do this in a formal proof. We want to show here that A is congruent to B mod M. By definition, that means that M divides their difference. So that's the thing we're chasing right now. So if A and B have the same remainder mod M, again, we're using the quotient remainder theorem, that's a different blue. Then A is gonna be equal to M times some quotient plus a remainder, and B will be equal to M times possibly a different quotient plus the same remainder. For Q1, Q2, and R in Z. Okay, so we have A mod M is equal to B mod M. That means they have the same remainder after you divide by M. So using the quotient remainder theorem, we can write A as M times some number plus R, B as M times some number, possibly different, possibly the same, plus R. where Q1, Q2, and R are all integers. So we're trying to get to a place where we can say that M divides A minus B. So we're gonna do A minus B, yeah? So then A minus B is equal to MQ1 plus R minus MQ2 minus R. That is MQ1 minus MQ2, which is M times Q1 minus Q2. Since Q1 minus Q2 is an integer, M divides A minus B. By definition, A is congruent to B mod M. Yoo-hoo! Any questions or comments about that?
This might be like when we did the strong induction thing where the first example was really long and complicated and made no sense. All the other ones made a lot of sense.
Oh, we're not doing any more examples. We're done.
Okay.
That might be our last, okay, sorry, we have 2 more proofs to do. But then that's it for the semester. This is stuff about mod that y'all are gonna use. This test is all computer science. Okay, not the equivalence relation part, but modular arithmetic is an equivalence relation situation. So really, that's all that we're doing.
We took this whole class for this.
That's right. No, that's not true, because a lot of that computer science exit exam is discrete math, so. Alrighty, yay. Okay, so, we're gonna find the integer A. That's pretty stressful for me. I just need you all to know that. We're gonna find the integer A so that A is equivalent to -15 mod 27, and A is between -26 and 0. I need a number that has the same remainder mod 27 as -15 and is between -26 and 0.
Same repeat.
That's what the equivalence, the congruence under that mod is, that A is congruent, or A mod 27 is equal to B mod 27, right? That's what we just proved.
26.
What's the remainder mod 27 of 26? 1, right?
Oh, we're, okay. I thought you wanted to like replace mod 27.
No. I want to replace the A with something that has the same remainder, mod 27 as -15. And is between -26 and 0. Yeah, it's -15. -15 has the same remainder as itself, mod 27, right? How would we know, how do we grow in this sense? How do we grow and keep the same remainder? Does that make sense what I'm asking you? How would you grow from -15? How do you grow to the next thing that has the same remainder, mod 27? Yeah, right. You're adding multiples of 27. That's how you're gonna get get other things that have the same remainder as -15. Is that making sense? Yeah, so we don't have to move. The -15 is where we need it, right? So A is -15 here. I need now an A that is congruent to 99 mod 41. So that means I need the same remainder mod 41 as 99. And I need for my number A to be between 100 and 140. So how would I maintain the same remainder mod 41 as 99?
18.
Say that differently, maybe.
Like odd.
Uh-huh.
It has to be the same, like we have to get the same with 99, like another value bigger.
Mhm.
Because it has to be,
So what do we add?
we have 41.
Yeah. Because adding the same number is gonna keep the remainder the same, right? We just wanna know how many 41s do we need to add? Well, we're at 99, so adding 141 will get us in the right window, right? Yes? And that keeps the remainder the same. Now, do you, if you would like, do you figure out what the remainder is, mod 41 of 99? But pass. Huh?
50.
You gotta go again, because it's gotta be between 0 and 41, right? I don't know, y'all, I'm not doing it.
No, I meant like that's the remaining.
Yeah, but it can't be
Wait, no, you're right,
51, yeah.
50.
You gotta go again. So what'd you say, 50 what?
Oh, right.
We say 58, so 17.
Yeah.
So you could do 17 plus multiples of 41 until you get to something between 100 and 140. Is 17 right?
Yeah.
Yes, okay, good. So we're gonna do 99 plus 1 multiple of 41. That's gonna give us 140. That's the number that we're looking for. Apparently that remainder mod 41 is also 17. I feel like this always goes really poorly in this class. Not for y'all, for any discrete class I've ever taught, but I don't know why. Is it me?
I think mod is just.
It's weird. Although y'all are doing better with it than has happened in the past.
I understand.
Good, good. Y'all are doing great with it. I am, normally this does not go well. Y'all are doing great. Okay, A is congruent to 24 mod 31, but we want A to be between -15 and +15. So we want the same remainder mod 31 as 24, but we need to be between -15 and +15.
You subtract
Yeah, what are we gonna subtract?
31.
Yep. So if we do 24 minus 31, what do we get? -7. Good. Do you have any questions? Right? Whitney, you were very quiet during that whole exchange. What do you feel?
I have no idea what's going on.
Okay. Well, this means that like 140 mod 41 is equivalent to 99 mod 41. That's what we're doing. But I'm just trying to get particular A values.
I guess I'm still confused. Like, when we wrote mod in a different way, I got it, but I forgot, like, I don't remember, like, mod is like 140 divided by 41 is the remainder.
Mhm.
I guess that makes sense.
Yeah, so the way that you do this is like, oh, so 99 is equal to 41 times something plus a remainder, which y'all are saying is 17. This number has to be between 0 and 41. If it was equivalent to 0 mod, this is the thing that it's equivalent to mod 41, whatever the remainder is. A mod is just the remainder once you divide by that number. So 99 and 17 have the same remainder mod 41. Remember when we did the Euclidean algorithm and we went all the way down with the remainders? We did like the next like line, we would have 17 is equal to something, something plus something. Yeah, this is the, I mean, it's the same kind of idea. Mod is, you know, doing that same sort of thing. Although the remainder is always 41. 17 here, sorry. I was thinking about something different. Okay. Does that make some sense?
It makes sense. I think my brain's just not comprehending it because I don't know like the big picture of like why.
Because mod is will be the most used equivalence relation that you guys have. Yeah. I mean, I think this is the like connection for, I mean, this is a pretty big connection for you guys with stuff. And is useful, right? Because if you can write a program that can handle like 99 and 17 in the same way or whatever, you know, like being able to write a thing where you have as little code as possible because your program reads something the same way or whatever, figuring out how to relate things so that your code is more succinct. Yeah, is better. So. Okay. Alessandra, you did some coding with math stuff, right?
Yes.
Okay, that, I don't have any follow-up. All right. All right, so we're gonna prove this theorem now. So M is a positive integer, the integers A and B are congruent if and only if there's an integer K, so that A is equal to B plus KM. Oh, there, I was like, what? These are congruent mod M. That is very confusing. There should be a mod M in here. Okay, so this is an if and only if statement. Now, I have never done an if and only if statement proof for you guys, or I did it all at the same time, but I'm gonna do that now. You know, normally we go this way and then we go this way. I'm gonna do it all at once because it's all definition, so they're all if and only if statements. We good? Okie dokie, let's do it. We have,
Always do this.
Hmm?
You can't always.
no, right, which is why I never do, but it's this one, I don't want to write this proof twice, so. It's the same forwards as it is backwards, so I don't want to do it twice. You do have to be careful when you write if and only if proofs that you're not saying things are if and only if statements that aren't. Okay. So we are gonna let A and B be integers and M a positive integer. Okay, so we're chasing definitions, yeah? A is congruent to B mod M if and only if. What's the definition of that congruence mod M? Definition. Yep. M divides A minus B. Okay, what does it mean for M to divide A minus B?
A minus B equals A.
So, yeah, M divides A minus B if and only if A minus B is equal to M times K for some integer K. This is true if and only if A is equal to MK plus B. We did it. Notice how each one of the times I said, like we would normally say then, or, you know, by definition, this means this. When they're definitions, they're if and only if statements, so you can do this proof this way, whereas this is true if and only if this is true, if and only if this is true, if and only if this is true. Alrighty, what do y'all think?
I don't think.
Oh, that's not good. We should be thinking. Yes? No? For our second to last proof to write in our note packets together, that's not a hard one. Marina, what's up? Equivalence relations, yep. That's all. But equivalence relations, yes.
When it says the integers A and B are congruent mod M, it basically just means A and then the congruent symbol.
Yeah. And because they're congruent, Whitney, you can do it like, you can do it either way. It doesn't matter. Yeah. Okay. Now, we've been saying this a lot, but like, we haven't actually shown that congruence mod M is an equivalence relation, so let's. We're not gonna prove it with a full proof, we're just gonna do scratch work, okey doke. What? Sky sent you something? This Sky, oh, okay, I was like, pay attention. Okay, congruence mod M is an equivalence relation, that's what we're gonna show right now. So we need to show what, to prove something is an equivalence relation.
Flexive, symmetric, and just.
All right, so for reflexivity here, what do we need to show? Let me write this in a thing for you. A is related to B if and only if A is congruent to B mod M. We're trying to show that this is an equivalence relation. All right, how do we do this? Yep. So we're gonna let A be an integer, right? What do we want to know?
Are we doing scratching?
We're not doing a proof. We're only doing scratch work.
Oh,
Is A congruent to A mod M? Yeah, because does M divide their difference? Yes, it does. So A is related to A and the thing is reflexive. Good? Yes, no? Okay. For symmetry, what do we get to assume? Yes, we're gonna let A and B be integers and assume that A is related to B. What do we want to show? Yep, that B is related to A. What do we have from A being related to B?
A is congruent to B mod M.
What does that mean?
M divides A mod M.
What does that mean?
A must be equal to.
Mhm. What are we trying to get to? How are we gonna get that? Can I just multiply by -1?
I guess.
But if I do it, I have to do it on both sides, right? Yes.
You could add everything.
You move,
Exactly.
yes. So because -k is also an integer, we have that M divides B minus A. And then from that, we get that B is congruent to A mod M. Which means B is related to A. We're doing it in backwards.
We are?
Yeah,
I feel like we did this exact same thing though.
but like before right now?
Yeah.
No, we haven't, I don't think.
Yeah, I think so.
There's no way.
We've done something like this before.
Well, I'm glad that y'all have you're so with it that it seems like we have, but we haven't. So we're gonna let A, B, and C for transitive here. We're gonna let those be integers. We're gonna assume what for the transitive property?
That A relates to B and B relates to C.
And what does that mean under this relation? Oh, sorry, we want to show that A is related to C. Okay, what do we have under this relation for A being related to B and B being related to C?
B equals C mod M.
What do we have from that?
Cut out the middleman.
Can't yet. Those are not equal signs.
M divides A minus B. M divides B minus C.
Yeah, but
C.
We need to get. Mhm. I think I'm gonna add. I think I'm adding, right?
Yeah, it's even.
Bless you.
oh, a system of equation.
Hmm. I don't have any more space. M divides A minus C. So A is congruent to C mod M, which means that A is related to C. Wow, I don't have any space for any of that anymore.
Shrink it.
Good idea.
Oh, no.
I'm gonna shrink just that A. Look at that. Oh my gosh.
Whoa.
Look at that little A that got dragged around here. There we go. Okay. We did the thing. It is an equivalence relation. Do you have any questions?
On the homework, there was one where I was trying to do the transitive thing.
Mhm.
And I got to this point where I had to like add up the equations.
Mhm.
On the right, I had 2 4s. Would that just become 8 down bottom?
Mhm. That was an equivalence relation.
Um,
Which was, what was the relation?
It was like 2 things become less than or equal to 4.
It's the absolute value, right?
Yeah, the absolute value.
It's not an equivalence relation.
I didn't think so. No.
It's not an equivalence relation. What? Mm-mm. You haven't yet. You turn it in Friday. It's not that much time. I did grade a whole other classes test, so sorry. I'll get your homework done as soon as I can. Y'all have turned in your crap late, like over and over and over again, so like maybe chill. I'll get it to you when I can. I have some grace here. What?
Did you see my email about that?
I don't know.
It was at like 3 AM one night.
Once I get them, I just move them into my discrete folder to grade later, and then I grade them when I need to. Other than this last homework, I believe I'm up to date on everybody's homework, other than homework 10, 11. Which one did y'all just turn in? 11. Other than homework 11, I'm up to date on everybody's homework, so. Or I believe that I am. All right. Ruth, what are you trying to figure out? What's what?
No, I think I figured it out. It
All
was
right.
C, the mod.
Yeah, this is C mod M. Mhm. Okay, so what do you think happens to sums and products under mod stuff? So 5 is congruent to 2 mod 3. Yeah.
They close on the mod.
Huh? 4 is congruent to 1 mod 3. What do you think 5 plus 4 is congruent to mod 3? 3, which is actually 0. Mod 3, right? It was a 0. This is 3, but 3 is actually 0, mod 3, no? mod 3. They both have a remainder of 0, mod 3. That's what congruence under mod is, yeah. So 9 is actually congruent to 0, mod 3. They're the same. You just add left side to the right hand side and it's really nice, works nicely, yes? Right? What about products? If 5 is equivalent to 2 mod 3 and 4 is equivalent if these things are true, this is not an if statement, these things are true, 5 is equivalent to 2 mod 3, 4 is equivalent to 1 mod 3. What do you think 5 times 4 is equivalent to mod 3? It's 2. Because 5 times 4 is 20. 2 times 1 is 2. But also 18 is a multiple of 3, so 20 is 2 off of that. So they both have a remainder of 2 mod 3. This works just like that. It's nice, right? Why did you make that face? You don't like it? You don't like the way I've written it? What's the problem? Huh? What's the problem? Tell me.
No, it's okay.
He likes his numbers written out in words.
No, it's nothing to do with the format or anything.
What is it to do with?
I reconciled it in my mind.
Oh, okay.
Association or something?
I was trying to think if you had to consider zero divided by zero. But you don't.
Because this part has to be positive. That's one of the, yeah. Alrighty, so what we just said is that if we're gonna put that now, this thing into letters instead. So M is a positive integer. If A is congruent to B mod M and C is congruent to D mod M, then A plus C is congruent to what?
B plus B.
Yeah. Good. B plus D mod M. A is congruent to B mod M, C is congruent to D mod M. What is A times C congruent to? Mhm. Okay, so what this means is that M divides their difference, right? So A plus C minus B plus D. And M divides A times C minus B times D. This is what we're gonna get to. We're gonna prove this now. You ready? Okay. So this is the first thing we're proving. This is the second thing that we'll prove. Oh my heavens. All right. So we have, we're gonna let M be in Z plus and A, B, C, and D be integers. Assume A is congruent to B mod M. And C is congruent to D mod M. So we're doing the first thing now, that A plus C is congruent to B plus D mod M. So we know M divides A minus B and M divides C minus D. Then there are integers K and L such that A minus B equals M times K and C minus D equals M times L. Now we're trying to get to a place where we can have A plus C minus B plus D. And if we add these two things, we actually have that. So A minus D plus C minus D is equal to MK plus ML. I'm going to rearrange the stuff on the left-hand side and I'm going to factor out an M from the right-hand side. I'm going to do this at the same time. But we're looking at A plus C then, and then minus that B plus D, because if I distribute that negative, I get a minus B minus D, right? Which is what I want. Oh, I wish those had lined up a little bit nicer. Let me move that down. Okay, so then you would say something like, since K plus L is an integer, M divides A plus C minus B plus D. Therefore, A plus C is congruent to B plus D mod M. And that is the proof of the first thing. So, and moving into that second thing, we're trying to prove the product thing. So A times C is congruent to B times D mod M. What I'm gonna do is go back up to use these two things. So recall, let's see, A is equal to MK plus B, and C is equal to ML plus D. Then A times C is MK plus B ML plus D. I'm trying to get to a point where I can say that AC minus BD is divisible by M, right? That M divides their difference. I'm gonna get there in a minute. I have an M squared KL, yuck, an MKD, and MLB, hey, and a BD. So I have AC minus B times D is equal to M times MKL plus KD plus LB. So since that thing inside those parentheses is an integer, M divides AC minus BD, and therefore AC is congruent to BD mod M. I believe that was our last proof to do together. Okay. Y'all ready to keep going? Ready? Are you ready? Yes, no, maybe? Not ready yet. When you have time to think through it. I just moved stuff around and then multiply. I just did a bunch of algebra. The last day of class, 23rd, 2nd, 3rd. We have Thursday, and then next week, and then it's the Tuesday after that. Because your final exam isn't until the Tuesday after that, April 30th.
That's still the Thursday before the last?
Is the last day of class, Tuesday. It's on the last day of class, yeah. And I'll grade your test and then give them to Julia, and you can drop by and get them from Julia so you can use them to study for your final. Okay. Good. Alrighty. We did this before, so we're not gonna keep doing it, but the equivalence class stuff, under mod arithmetic, it divides the thing. So if you're looking at mod 5, remainders mod 5, this is all the multiples of 5. Remainders mod 1 or all the multiples of 5 plus 1. The equivalence class of 2 is all of the multiples of 5 plus 2. Y'all get this? Yes? Now, eventually, all of these numbers, all of the integers will fit into one of those equivalence classes and only one of them. And when that happens, you can look at just representatives for these things. So you have, because everything has one of these 5 remainders, you can sort of just like sort of pretend the set is just those things. So the integers mod m is written as z sub m, so it's all of the remainders mod m. These are cyclic groups of order m for anyone who is going to take abstract algebra or has taken abstract algebra. What? I know, but there's two people in the back of the classroom have had abstract algebra. And YouTube will take abstract algebra, so. Whoop, whoop. Alrighty, good. Okay, so, addition and multiplication mod m satisfy almost all the same properties of ordinary addition and multiplication. Yeah, so if a and b are in zm, then a plus b mod m should be in zm. A times b mod m should also be in zm.
So basically you're saying that there's the same equivalence classes?
No, they're not the same equivalence classes, but that they take, I don't know, 1 and 4, right? And Z5, take 1 and 4, that's 5. The remainder mod 5 of 1 plus 4 is 0. That's in Z5. That's sort of how it works, right? So under mod stuff, it's closed, right? So when you multiply two things in there, that product mod 5 should be sitting inside the set as well. All right, so the additive identity, if something is an additive identity, if you can add it on the left or the right, you're like, why does it matter what order, what side it's on? It will matter later. So if you're adding things, an additive identity under these things is just 0, and that's in all of them, so it's there. You want to be able to add something and get back the thing you started with, so adding 0 is the right call in this situation. Additive inverses, you would like to be able to add something to your element and get to 0. Multiplicative inverses, you would like to be able to multiply your element by something and get to 1. So these sets always have additive identities and inverses, but they don't always have multiplicative inverses, and we'll talk about why. So in Z7, so remember, this is all the remainders mod 7. So what does Z7 look like? Yeah, it's 0 through 6. The additive inverse of 4 is 3 because 4 plus 3 is 7, and the remainder mod 7 of 7 is 0. Yeah. So the additive inverse knocks you back all the way to 0. It cycles you back to 0 in these cyclic groups here. Okay, so in Z7, the multiplicative inverse of 5 is 3. So a multiplicative inverse, I would like to get to 1. 5 times 3 is 15. 15 mod 7 is 1 because 14 is, you know, a multiple of 7. We good? Yes? Sort of? You understand what's happening? Yes, for the additive inverse, you want to have in the mod stuff, right? Because we're under NZ7, this is mod 7 stuff. So yeah, you're looking at the remainder. These those representatives are the remainders mod 7. So for an additive inverse, you want to get to 0. So you want no remainder, mod 7. For the multiplicative inverse, you want a remainder of 1, mod 7. So in Z6, I would like to be able to show that 4 has no multiplicative inverse. That means I want to, so what does Z6 look like? So I would like to take 4 and multiply by something and get 1 mod 6. Yeah. So 4 times 0 is 4. Well, that's not it. 4 times 1 is, oh, that's 0. 4 times 0 is 0, not 4. It's fine. 4 times 1 is 4, which is also not equivalent to 1. 4 times 2 is 8. Mod 6, what is that equivalent to? What is 8 equivalent to mod 6? How far off from a multiple of 6 is 8? 4 times 3 is what? 12. What is 12 equivalent to mod 6? Four times 4 is 16. What is that equivalent to mod 6? And 4 times 5 is 20. And what is that equivalent to mod 6? Which is equivalent to. Mhm. So what we were looking for a multiplicative inverse there is a 1 in any of these spots. And we don't have one, right? Okay. So 4 does not have a multiplicative inverse. Can I ask you a question? Why do you think that is? It is part of that, yeah. These are both even, and really it's that they're not relatively prime. So the greatest common divisor for these is 2, not 1. So we can't get a remainder of 1 because these are gonna move, all your remainders are gonna be moving by 2s, by multiples of 2. If the GCD of these two things was 1, then you would have a multiplicative inverse.
So does that mean that times?
So like 5 would have a multiplicative inverse in here. 3 doesn't. 2 doesn't,
Oh, and 3.
because 3 and 6 have a divisor of 2, right? Common divisor of 2. Does that make sense?
That makes sense.
What?
You said 3 and 6 have a common divisor.
Right, of 3. They are both, 6 is 2 times 3. 3 goes into both. So that's why it wouldn't, their remainders are gonna move by 3s, not by 1s. Yeah. Okay. Y'all are not ready to do your next homework assignment yet because it's got stuff from 12.1 and 12.2, which we haven't done, but you can do the equivalence relation stuff and the 8.4 stuff. So I would go ahead and knock that out before Tuesday because I'm gonna make your homework due pretty quickly. Okay, that's half the homework, would be stuff that isn't 12.1 and 12.2. So go ahead and do that.